back down for the non-live days?
No, but I record live class just to make my life easier.
No, you have to have your camera on.
What do you mean?
Like you have.
Oh, no, they can do whatever they want. They can leave right now if they want. If they want to go home.
Like you have to have it on, otherwise the teachers have to absent. I just wasn't sure if you were also making that rule when it was
That's
not.
right.
No.
There's a violation of privacy.
Oh my gosh, no, it's not.
It definitely felt like it, because it's 8 a.m.
No, okay, time out, you baby. Elementary school has been forcing every single child to always have their camera on since day one. There's no reason why a middle schooler or high schooler can't have their camera on. You just want to hide so you can sit on your phone and not focus. That's literally, that's what most of it is.
What else?
Well, like, when I wake up fresh in the morning, I don't want to take, like, change my mind.
That's stupid. That's fine.
Okay.
No one's looking at you. Like, everyone thinks they're looking at them in the meet. No one's looking at you. No one cares. Okay. So the recording started. Sorry, if you're watching the recording, I apologize for the excellent intro here. Let's jump into 6.9. This is the very last topic of Unit 6. I think you'll kind of enjoy it. It's a little puzzly. It's kind of fun. We'll start slow and then we'll build it up towards the tail end of the class here and give you a couple harder examples. But this is, I don't know, it's a pretty fun topic. I like this. One of my more favorite topics all year. So, I don't know, just my opinion, I guess. But this is on Hess's law. So Hess is the last name of a dead white guy who gets credited with, doing this. So let's talk about what's going on. We're still dealing with enthalpy. Okay, so we're still dealing with delta H in all of our examples. And this is a third way of finding the overall enthalpy for a reaction. Monday, we dealt with bond energies. Okay, we calculated all the energy of the bonds on the reactant side, calculated all the energy of the bonds on the product side, and then got a total to get the overall enthalpy for a reaction. Yesterday, we did the enthalpy of formation. We gathered the information on the enthalpy of formation on the reactants, the enthalpy of formation of the products, took the products total minus the reactants total to get the overall enthalpy of a reaction. So we figure out two ways to do this. Today's a third way. This is called Hess's law, and we'll start with a pretty simple example. Okay, let's pretend we have that reaction up above. B, A, and E are very clearly not real elements. They're just placeholders, just a generic example of how Hess's law works. Okay, so this is the overall reaction, and this overall reaction has an enthalpy of positive 9 kilojoules, meaning it's endothermic, and it's going to take in, or that energy is coming into that system throughout that process. Okay, let's take these three steps, or these three reactions, and let's add them up. Okay, go ahead. This is similar to mechanisms, like we did in Unit 5. Okay. But let's combine these three steps into an overall process. Wait a second. Oh no. Right? What do we get for the overall process? Hey, the same thing as that. Now, each of these reactions has an enthalpy. If I were to take and add up their enthalpies, we get a total enthalpy equal to positive 9 kilojoules. Okay? What do you notice? Okay, even though these three steps or these three reactions are separate, their net result is the exact same. And as a result, the net enthalpy change of those three steps is the exact same as the original reaction would have been all by itself. Okay. So what you notice, delta H is the same. Okay. So here's the takeaway. Here's what Hess's law is. Here's what Hess's law says. Okay. Hess's law states the heat evolved or absorbed in a chemical process is the same whether the process takes place in one or several steps. This is also sometimes called the law of constant heat summation. Basically saying if you have multiple steps, but they overall equal a different reaction, right? You can add up the steps and it'll equal the overall enthalpy of the reaction. That's the concept. It's pretty simple. Okay, so let's try a real one. I have N2 plus 2O2 yielding 2NO2. Okay, here's two reactions. If I combine these reactions, I get the same process, right? Okay, and then the overall enthalpy change, I would just combine these two, and I get the exact same enthalpy. Easy peasy. Okay, so Hess's law states this. It doesn't matter if this happens in one step or whether it happens in multiple steps. If the net result is the exact same chemical equation, the enthalpy will be the exact same. And you can figure that out by adding or combining the enthalpy of the steps. Okay. This has been very easy so far, I hope. Let's spice it up a smidge. Okay. Here's a reaction. I want to turn graphite, pure carbon, into diamond, pure carbon. And I have these two reactions that I know. Now, you'll notice this reaction has graphite plus oxygen, gives me CO2 plus 394 kilojoules. Sometimes the enthalpy is just written in the reaction. Okay? If your enthalpy or your energy goes on the product side, that means it's being released. So delta H would equal a negative 394, right? Sometimes if the energy term is on the reactant side, that would just mean your enthalpy is positive and it's endothermic. Okay? If you want to ignore these in the reaction, you totally can because it's already written over here. Just understand that if the energy is written as a part of the chemical reaction, if it's on the product side, that means it's being released. It's a negative term of enthalpy, or an enthalpy is being released. Make sense? Okay, so I want this reaction. If I combine these two reactions the way they're written, how's that going to go? Well, if I combine them the way they're written, I'm going to get graphite plus diamond plus 2O2 gives me 2 CO2. I don't want that. Right? What can I do? Huh? Yeah, let's flip one. It's totally allowed. Okay? I want graphite on the reactant side. We're good. But I want diamond on the product side, right? So let me take this reaction, the second one, and flip the whole darn thing. And make CO2 my reactant, and diamond and O2 my product. If I flip the whole reaction, what do you think is going to happen to the enthalpy? It's going to get flipped. Instead of being released, right, it would now be on the reactant side and it would have to be added. So if I need to flip a reaction completely backwards, change the products to reactants, reactants to products, I also have to change the sign of my enthalpy. Makes sense? And we can do that. Okay? I think it's on the next slide. Sure it is. Okay? We add them up the way they're written, it's not going to work. So what do? We want diamond on the product side. Let's flip it. If we flip it, okay, now if I combine these, right, I'm going to cross off my oxygen. I'm going to cross off my CO2, and I'm going to get graphite turning into diamond. That's what I want. Now, the energy terms are also written in here again. They would cancel each other out too. If you wanted to keep them as a part of the chemical equation, totally can. I would cancel out all 394 of that and be left with just 2. Okay? Okay? Graphite to diamond. And then the overall enthalpy change is just going to be 2 kilojoules. Because now I have flipped the second one, so instead of having the the negative 396, I would have flipped it to make it a positive 396. Negative 394, positive 396, because we have an excess of 2. Okay, still easy, right? By the way, I'm going to finish super early. Okay, still easy, yes? Let's spice it up some more. I want to find the enthalpy for this reaction. Okay, 2 boron plus 3 hydrogen gas yielding B2H6 gas. I have these 4 reactions to deal with. I'm going to need to mess up some things. Okay? In order for these 4 steps to give me that reaction, if I leave it the way it is that going to work? Look real quick. No, it's not. Right offhand, I can see that I have B2H6 as a reactant here when I want it as a product up here, right? So that's not good. Okay, let's start messing with this. Let's start fixing our steps so that when we add them together, we get the overall process that we're actually interested in. 2 borons. I want 2 borons on the reactant side. The only place that boron all by itself shows up is the first step. And hey, there's 2 of them. I think we're good. We are not going to change the first step ever from here on out. Because if I do, right, if I flip this, now I've got that on the wrong side. If I double this or cut it in half, now I've changed how many I want. This first step is locked in. We're not going to change it. We can't change it because it has exactly the right quantity on the right side. I'm going to skip the hydrogen, although I don't have to. Never mind. Let's not skip it. I want 3 of them. Hydrogen shows up in 1 reaction. There it is right there. It's on the right side, but I need 3 total, right? So let me take this reaction and multiply it by 3. I want this step to occur 3 times total. So I can get the 3 hydrogens that I need in my overall process. If I multiply this reaction by 3, or in other words, if I have this reaction occur 3 times total, what's going to happen to the enthalpy? If it happens 3 times, I'm going to release negative 286 3 times. So I also have to multiply this by 3. Last but not least, I need B2H6 on the product side. It only shows up in step 2. It's the only place it exists, so I know I'm going to have to mess with this one. And I need to flip it. Okay. However you want to signify this, if you want to cross this off and rewrite it down below, because it's easier for you to visualize that, please do that. Okay. I tend to not, just because my brain is weird. I do it like this, and I just write flip. I wouldn't recommend that for everybody. Okay. I would strongly recommend, if you're much more comfortable or much more confident just crossing it off and rewriting it below, backwards, do that. Now, if I flip this, what happens to my enthalpy? Sign changes. What was normally exothermic is now going to be endothermic. All right. So I have my 2 borons. I have my 3 hydrogens. I have my 1 B2H6 on the right side now. I'm good, right? What about all the other junk? Well, we need all that other junk to cancel out, right? It has to cancel out. Otherwise, we don't have this. The end goal is that reaction. That's what we want. Any additional or extra stuff we don't want there. So we got to make sure that everything else that's not supposed to be there goes away. Right? So, fractional coefficients, that's not fun. Let's take a look. So if let's see, I have 3 halves oxygen on the reactant side, plus another 3 halves oxygen on the reactant side for a grand total of 3. Okay. Now I also have 3 oxygen here, but that one got flipped, right? So the oxygens are going to cancel out with the way I have this written so far. Because I have 3 halves on the reactant side, and a grand total of 3 on the product side, they're gone. That's good. I have 1 B2O3 and another B2O3. This one got flipped, so they're on opposite sides. Those will cancel. Okay, so far so good. 3 water vapors, or 3 waters in the gaseous phase. These were flipped, so they're actually on the reactant side. If I go down to the 4th step, I have water gaseous on the product side. That is 3. This is 1. I think I need to triple that. You following my logic? You hanging with me? Okay. From this step, I have 3 waters in the gaseous phase on the reactant side, because this one was flipped. I don't have any water in my overall process. I want that all to get canceled out. I want it all gone. So I got to find the other water vapor somewhere in this process. It's in the 4th step, but I only have 1 on the product side. I want 3, so I'm going to triple the 4th step. Last but not least is water in the liquid phase. We already tripled this one, so I have 3 waters on the product side in the liquid phase, and we already tripled this one, so I have 3 waters in the liquid phase on the reactant side. I think we're good. Since I tripled that reaction, I also need to triple that enthalpy. And now it's just a matter of double checking our work. Okay? So, 2 borons. The oxygens, 3 halves, 3 halves, 3 on the other side. These will all go. I have B2O3 product side. This got flipped, so B2O3 reactant side. Those cancel. I have 3 waters in the gaseous phase, 3 waters in the liquid phase, and I think we're good. So 2 borons plus hydrogen gas. How many do I have? 3 of them. Yielding 1 B2H6. So you got to mess with it, right? You got to mess with these reactions. You got to flip them, you got to double them, you got to cut them in half, you got to do weird things. But when it's all said and done, however we changed these, I flipped this, this is times 3, that's times 3. I have to do those exact same changes to the enthalpy. Because if I flip the reaction, I've changed it from exothermic to endothermic. if I've tripled the reaction, it happened 3 times. So now I have to triple the amount of energy released. And so on and so forth. So let's add this up. What is the overall enthalpy change for our 4 steps? So I'll jump at once. Oh, you did it already. Oh, good. Thought you were all like just staring at me like, no, I don't want to do that. Positive 36? Cool. Any questions? That's Hess's law. Okay, couple reminders. If you flip the reaction, you got to flip the enthalpy. If you need to multiply by a coefficient, you also have to multiply the enthalpy by a coefficient. Okay, now we're getting extra spicy. My favorite among spice. Extra. The female rap group? Never mind. Yes, like salt and pepper. That's extra spicy. This one's really, really funky. Okay? Yeah. Correct. And this is the overall reaction that I want, but I've given you no reaction steps. No.
That's a wrap. I think we're good.
Combustion reactions involve reacting a substance with oxygen gas. When compounds containing carbon and hydrogen are combusted, blank and blank are the products. What do you get when you burn hydrocarbons? Water and CO2. Yep. Using the enthalpies of combustion. What do you think that would mean? What is an enthalpy of combustion? What's that trying to imply? What's the word enthalpy mean for us? Heat. What's combustion mean?
Fire.
Fire. So an enthalpy of combustion is how much heat is released when it burns. Makes sense, right? We had to break it down into like less sciencey words, but literally that's what it is. How much heat is released when you burn this stuff? Okay? When you burn C4H4, you get negative 2,341 kilojoules of energy per mole. In other words, you release 2,341 kilojoules of energy per mole of that stuff that you burn. For C4H8, you get 2,755 kilojoules of energy released per mole of that stuff you burn. And for hydrogen gas, you get negative 286 kilojoules of energy released when you burn a mole of hydrogen. So, what we're going to do, we are going to write out the combustion reactions of this, that, and this, and then use those 3 steps, manipulate them to get this overall process. Okay? It's fun. This is like the greatest problem all year. You're not as excited as I am. It's puzzling. It's fun. I don't know.
I don't see it.
It's not making me smile yet.
No.
I haven't stopped smiling. Okay. So C4H4.
Enjoy it. That's good.
You gotta have something, right? Okay, so C4H4, we're gonna burn it. What's the other reactant? O2, yes. What do you get for products? Yep, CO2 and H2O. What? Excellent. The combustion of this, I'm going to move this over. Gosh darn it. Oh, yeah, I could grab it. Pro tip. I always forget about that feature. Aw. Okay. So there's my reaction. The enthalpy of this one is negative 2341 kilojoules per mole. Okay, I'll just leave it as kilojoules. Is this balanced? Nope. That looks good, right? That's our first step. Let's do the next one. We are also going to burn C4H8. What's the other reactant? Uh-huh. What are we making? Is it balanced? Of course not. Go for it. We're burning more stuff. When I burn hydrogen gas, what do I get for a product? Do I get any CO2? You just get water. Yeah. Yep. Can't make any carbon dioxide if I don't have any carbon, so we just get the water this time.
So how are we burning gas? I'm just curious. So, like, I don't know. When I think of like burning, it's like a log and something I can like see and it happens over like a slow period of time.
Sure.
Like burning is like gas. Like when you
Well,
light,
sort of. I mean, like a
like
bullet
when you
right?
like methane or whatever.
Yeah.
It just like goes and stuff. Unless you like keep it streaming going.
Yeah.
It's like
Or if you have like,
constant reaction that's happening.
or if you have it under pressure, right? Where like you have like again like liquid propane turns into like gaseous propane for a gas grill, right? And like it's just under pressure, so if you open the valve, it's just constantly supplying more and more propane to burn. But yeah, in this instance, I mean, this is more hypothetical paper pencil than it is like we're actually burning these three things. Yes, Sam?
Do you ever, if they make water, do you ever try to find like hydrogen gas deposits in the earth and burn them to get drinkable water? Too much energy.
So hydrogen gas is pretty tough to contain because obviously, like if it's open to the atmosphere, it's gone. But yeah, it would totally work in theory. Plus, in the process of burning it to turn into water, you would obviously get some energy out of that too. So the theory behind it's not bad. I can't imagine there's a whole heck of a lot of hydrogen gas to be found out there in nature. There's got to be some, but it can't be a ton. And the instant it gets exposed to the environment, it's just going to be gone and up and out of our atmosphere. So the enthalpy of this is negative 286. Is this balanced? Nope. Now, it releases negative 286 kilojoules per mole of hydrogen we burn. After we've balanced this, how many moles of hydrogen have we burned? 2. That's an issue, right? This is a lie. We've already balanced this, but when we balance it, we have 2 moles of hydrogen, not 1. So on a per mole basis, it's 286, but I don't have 1 mole. I've got 2 moles. So let's double that. What's double of negative 286? 572. If I can do math, is that true? Okay. We had to fix that. Does that make sense, right? We released 286 per mole. We burned 2 moles, so now we have double 286 just instantly off the bat before we start doing Hess's law nonsense. All right, now you got your steps. Let's combine these 3 steps so that they equal this. It should be pretty darn easy, actually. This is the easier part in this example. The Hess's law stuff is easy for this one. It was more so the combustion stuff that was unique. Go for it. Do Hess's law if you could. And give me an overall enthalpy. Sounds about right. What do we need to do?
What's the second one?
And when we do so, that changes. Yeah, and that's it. Okay, that's it. So I end up with C4H4, sorry. Let's cancel things off first. I'm sorry. 5 oxygens on the reactant side, 6 oxygens on the reactant side. This got flipped, so we have 6 oxygens on the product side. 4 CO2s on the product side. That got flipped, 4 CO2s on the reactant side. 2 waters on the product side, 2 more waters on the product side, 4 waters on the reactant side. And the overall process is going to be C4H4 plus 2H2, giving us C4H8. And the enthalpy change for this process should equal all that stuff added up. And it was negative what? And that's Hess's law. Are there any questions at all? Again, the process is pretty straightforward, right? You've got multiple reactions. You can add them up to get a different reaction. And when you do, the enthalpy of all those individual steps will add up to the enthalpy of the overall reaction. In order to sometimes get the steps to match the overall, you have to flip things. You might have to double things. You might have to cut something in half if I'm feeling extra mean. I think there's one on the review sheet that's pretty mean or fun. I don't know, your definition. Okay. But that's all I got. That's Unit 6. You have homework topic 3 due on Friday. Thanks. You have homework topic 3 due on Friday. You have a test on Monday. Tomorrow, we will review in class. You have a review packet with an outline of all the topics and bulleted points of all that good stuff. And you have an in-class review. The in-class review we'll work on together tomorrow. The other review sheet is your resource to get ready for the exam on Monday. If you want, because we just did Hess's law stuff, go to your regular review. There should be a nice Hess law problem in there. I don't think I have any on the Do I have a unit 6? I've got to have a unit 6. I don't know if I have any Hess's Law problems on topic 3. I don't think I do. I don't think I do.
You said yesterday, we now know everything to do.
Just this stuff.
Yeah, so, yeah, topic 3 is just using bond energies and using the enthalpies of formation. By the way, if you need the enthalpies of formation, I did post the PDF of those copied sheets from the textbook. So please use that. Yeah, we'll deal with the in-class review together. The regular review, there's got to be a good Hess's Law problem there. Ooh, there is. Yeah, that's the nasty one. Problem number 3 on the regular review. If you want to just stick with Hess's Law stuff, take a look at that right now. If you prefer to work on your homework, that's fine too. But again, for your homework, you're going to need those appendices from the textbook, so you might need to bust out a Chromebook. I have one book with me. If you want to borrow that while you work, that's fine too. People at home, you're welcome. You're free to go. You can have a great day. Thank you for joining me. I appreciate it.